Now let's take a look at Thomas Telford's later works. We started to look at the Craigellachie Bridge, completed in 1814, spanning 150 feet. Next, we're going to look at the Myth Bridge, completed in 1824, at about the same span, 170-foot span. And then finally, the Menai Bridge, completed in 1826. This is not an arch, this is a 580-foot suspension bridge. With the design of the Craigellachie, Telford noticed that he made what he would call essentially a mistake, and he corrected this with the Myth Bridge. If we look at these two bridges, we see that the landscape is different, so you might notice they are different bridges by the landscape. But if you look at just the bridge itself, can you notice the difference between the two bridges? Because they are very similar to one another. The difference between the Craigellachie Bridge and the Myth Bridge is in the spandrels. It's in those diagonal members that connect the deck to the arch. If you look closely at those diagonal members, you'll see that they're oriented differently in the Craigellachie versus the Myth. In the Craigellachie, if you take the bisector of those diagonal pieces, you'll see that that bisector is normal to the arch. It's coming perpendicular to the arch. Whereas in the Myth Bridge, the bisector of those diagonals is vertical. It's completely straight up and down. In the Myth Bridge, this is a more efficient way of carrying the loads. The loads in those diagonals are more efficiently or more evenly distributed between those diagonal members. Whereas in the Craigellachie Bridge, in particular, those diagonals that are leaning or more horizontal are carrying much less load than the diagonals that are more vertical. Now we come to the Menai Bridge, completed in 1826, a 580-foot span suspension bridge designed by Thomas Telford. Now there was a need to design this bridge, and the need arose from the Act of Union of 1800, which merged the Kingdom of Ireland with the Kingdom of Great Britain. They needed to connect London to Dublin, and to do that you had to go through the island of Anglesey all the way to the tip of Holyhead, and to get to Holyhead and even Anglesey you had to cross the Menai Straits. If we look at the side spans of this bridge, we see that it has both arches and suspenders. And this again is ambiguous. It doesn't tell you clearly how those loads are being carried. But Telford did this because he was concerned about wind. He wanted to make sure the back spans were heavy and anchored. Just before the bridge opened, Telford's resident engineer noticed undulations from gusting winds. So Telford added bracing, which cut down the movement. 10 years later, about 2 years after Telford's death, the bridge keeper reported large oscillations, and unfortunately no action was taken, and in 1839 a gale tore part of the roadway loose. Telford's writings in 1820s and his resident engineer's field observations showed how horizontal wind can cause extensive vertical motion in a suspension bridge. Unfortunately, this lesson in history was lost in the bridge designs to come, as we will see. In the Menai Bridge, although the towers look heavy, they're actually hollow, like in the Pont-Casiltib Aqueduct Bridge. So Telford, again, is thinking about efficiency in his designs. Let's use the Menai Bridge to define some terms for you as related to suspension bridges. The first term that we have to understand is span. When we talk about a span of a bridge, we're talking about the longest unsupported length, and for suspension bridges, that distance is from one tower to the next. Next, let's look at the cable. The cable goes from anchor to tower to the next tower to the next anchor, and it is in tension, and it's in tension due to the uniform loads imposed by the hanging suspenders. The suspenders are the vertical elements that suspend or support the deck. The form of that cable is parabolic. I'm going to do a brief demonstration for you to show you the shape that these cables take when loaded, and it'll give you a better sense for why the form of the suspension bridge cable is parabolic. In this demonstration, this chain represents the cable of a suspension bridge. We know that the chain can only take tensile forces. It can't take any compression forces. It can be stretched, but it can't be squeezed. So let's look at how the shape of this chain changes when we add loads. So if I add one load right in the center, we see the V shape that this chain takes. But if I'm going to add continuously load along this whole chain, we're going to see it start to take the form of the cable of a suspension bridge, which is a parabolic form. All right, so now you start to see the shape change a little bit more. So these weights represent essentially the load that's transferred from the suspender, which is the vertical element of a suspension bridge, to the cable. And it's the load represented by the weight of the deck. And we see that as I add more and more of these loads along the chain, we're starting to see that parabolic form take shape, which is the shape of the cable in a suspension bridge. Telford designed his bridges for carriage loads, but the railroad age was approaching, and that is where we move to next.